Welcome to the lecture series of Mathematical Modeling of Manufacturing Processes. I am Dr. Suman Gotwal, working as an assistant professor in the Department of Mechanical Engineering at Ajay Kumar Garg Engineering College, Ghaziabad. So, in today's lecture, we are going to start about the mechanics of orthogonal metal cutting and force component analysis. It is a very important topic from the exam point of view. So, these will be the outline during this lecture. First of all, we are going to discuss about the different force component which will act during the cutting operation. Then we will see what are the assumptions that we should make when we want to study the merchant circle. Then we will discuss the merchant circle in detail. After that, we will do the force analysis. The components which we are finding here, we will do the analysis of those force component here, and then we will see what is the merchant first equation. Okay. So, in the coming slides, we will discuss these topics in detail one by one. So, first of all, the force components. So, as we have already discussed that when we talk about the orthogonal cutting, orthogonal is a two-dimensional cutting, okay, and it is easy to analyze the force components as compared to the oblique cutting. So, here we are talking about the orthogonal cutting only, okay. So, we have already discussed this diagram. I am again explaining it. So, we can see here, this is our workpiece, this one, okay, this is our workpiece and this is our single point cutting tool, okay, this is our single point cutting tool. As we know that this surface or the back surface of the tool is known as the flank surface of the tool, and this is the machine surface. So, the angle between the flank surface of the tool and the machine surface is known as the clearance angle, or we also call it the relief angle, okay. Now, this is the rake surface of the tool, or we can say it is the tool face. We can say it the rake face of the tool, okay. So, the angle between this rake face of the tool and the perpendicular to which? To the feed motion, direction of the feed motion is known as the rake angle, and we specify it with the symbol alpha, okay. And here we have the positive rake angle, okay, this is the positive rake angle. Now, what is T naught? T naught is basically the uncut chip thickness, okay, and this is our shear plane. This is our shear plane, you can see here, this is our shear plane, and this shear plane, the angle between this shear plane and the direction of the feed motion is known as the shear angle, and we denote it with the symbol phi. Clear? Now, we can see here that this chip is flowing over the rake face of the tool, and the chip flow direction is this one. Now, it will have some thickness and we denote it with the help of TC. TC is basically our chip thickness. Clear? So, these are the terms which we should know before the analysis. Now, in this diagram, we will see what are the different types of forces that act during the cutting operation. So, in this diagram, we can see here, first of all, we will see the rake face of the tool, and this is our rake face of the tool, okay, and over this rake face, the chip will slide. So, when the chip will slide over this rake surface, there will be friction at the chip tool interface, okay. It means that a friction force will act along this rake face of the tool. So, we have specified it with the help of symbol F. So, F is basically the friction force. We can see here that friction force F. Now, because we are talking about the orthogonal cutting, and it is a two-dimensional cutting. So, one force is acting, means F force is acting, but actually they can incline at any angle. So, what we do for the simplification, we resolve into the vertical and the horizontal components. So, we are doing the same here also, that F is our friction force which is acting towards the tip of the tool. So, one force must be here which is acting perpendicular to this friction force, which is denoted by N. So, N is the force which is normal to the friction force, and R is the resultant of F and N. So, R is the resultant force. So, we can see here friction force F and normal force to friction is N. Okay, these two forces are acting along the rake face. Now, we will come to the shear plane. So, shear plane is the plane along which the deformation will take place. So, the deformation of the workpiece is taking place along this plane. So, one force, that is the shear force, will be acting along this plane. So, its direction will be this. So, Fs is basically our shear force. So, if Fs is acting in this direction, so there must be one force which is normal to this shear force, which is known as Fn. Okay. So, we can see here shear force Fs and normal force to shear Fn are acting here, and R dash is the resultant of these two forces, Fs and Fn. So, we have discussed four forces which are acting during the cutting operation. Now, as we know that the tool is feeded in this direction, tool is moving in this direction. So, there must be a cutting force along this direction. So, cutting force will be like this, and we denote it with Fc. Fc specifies the cutting force, and we also call it horizontal force, and we specify it with the FH. FH is horizontal force. Now, this is the cutting or horizontal force. So, one force must be here which is perpendicular to this cutting force, and this force is known as the Ft or Fv. Fv is basically our vertical force, or Ft is thrust force. Okay. So, these six forces act when the cutting operation takes place. Okay. So, here we can see vector addition of Fn N is the resultant R, and vector addition of Fs and Fn R is resultant R dash. Okay. Now, we come to the cutting and the thrust force. So, we have already discussed these two friction force and these two forces which are due to the shear plane, along the shear plane. These cannot be measured directly. So, in order to measure these forces, the forces acting on the tool to be measured initially. Okay. So, force which are acting on the tool are basically Fc or Ft. So, we have to measure the cutting force or the vertical force first if we want to measure these friction or the shear forces. All these forces can be represented at the tool point in place of their actual point of action. Okay, and these forces may act at any part of the tool, but for the simplification we are considering this, that all these forces are acting at the tip of the tool. Okay, in place of their actual point of action, and by doing so, it is possible to construct a cutting force circle which is known as the merchant circle. So, all these forces will come under the merchant circle. So, for merchant circle, we are assuming that all these forces are acting at the tip of the tool. Okay, and for this merchant circle analysis, basically the thin you can see here this minimum energy principle is considered. what is minimum energy principle? According to this principle, the minimum energy will be required to deform the workpiece along a plane which is known as the shear plane. It means the shear plane will be located at a place where minimum energy is required to deform the material. So, this merchant circle theory is basically considered the minimum energy principle, and this thin zone model is basically useful for the analytical purpose. Okay. Now, there are some assumptions that we considered in case of the merchant circle. So, what are these assumptions? First one is the tool edge is sharp and there is no contact along the clearance surface. Tool edge is sharp, it means it is not blunt, it is very sharp. Cutting edge is sharp, it means the less forces will be required to deform the material, and there is no contact along the clearance surface, means there is a angle is provided between the flank surface of the tool and the machine surface, which is known as the clearance angle. So, clearance angle is provided. So, rubbing between the flank surface and the machining surface will not take place, and it will make the cutting operation possible. Okay. The work material undergoes deformation across a thin shear plane. So, we have already considered this assumption, or we have already discussed this assumption that we are considering the minimum energy principle, or we are considering our shear plane as a thin shear plane along which the material is deforming. Next is there is uniform distribution of the normal and shear stress on the shear plane. So, the plane along which the deformation is taking place. So, there the forces are acting, stresses are producing. So, these are uniform in nature and these are uniformly distributed along this shear plane. The work material is rigid and perfectly plastic. Work material is not flexible. We are not taking the rubber-like material which will change its shape when we apply force to it. So, our work material is rigid and in nature and it is perfectly plastic. It will go under the plastic deformation. The width of the tool is greater than the width of the work. So, why it is necessary? So that the material is removed in a single pass from the complete width of the workpiece. That is why we will consider the width of the tool greater than the width of the work. A continuous chip is formed without any built up edge or BUE. So, we know that in case of the ductile material, continuous chips are formed, but when the factors are different, for example, if cutting speed, feed, use of the cutting fluid, rake angle, these are the parameters basically which are responsible for the type of the chip produced. Okay. So, if we are changing these parameters, then in some cases continuous chip will be produced and in some cases the continuous chip with built up edge will reduce. But in case of the continuous chip with built up edge, we will not get the good surface finish and higher cutting forces will be required. Okay. So, we are considering here only continuous chips are produced here. The chip width remains constant because during the derivation or the analysis of the forces, we will use the term TC, which is the chip thickness. Okay. This is the chip thickness. So, we are considering it constant, so that the number of variables which will be involved in the analysis we will keep it at minimum. The chip does not flow to side or there is no side spread. So, as we know that the chip flows or slides over the rake face of the tool. So, we are considering here that the chip is flowing only on the rake surface of the tool. There is no side spread. Okay. And the last assumption is that the volumetric change of the material during the machining is 0. So, we are taking the depth of cut very small, so that there is no volumetric change in the material. Means volume before the cutting is equal to the volume after the cutting. Okay. So now we come to the merchant circle. So we have discussed all these forces in the previous slides. I am again explaining these. This is our tool, okay, and this is the rake surface of the tool. So the force F is acting along this surface. So we have extended this line, and you can see here this force is mentioned here. Now one force which is normal to this friction force act, we took it like this, N. We denote it with the help of N. So we have specified it here, N. You can see here N. So all these two forces are here, and the resultant of these forces we have already discussed in the previous slide, that it is R. So you can see here the resultant of the F and N is R. Okay, and the angle between these friction forces F and N is known as the friction angle, and we denote it with the help of beta. So beta is our friction angle. Now we can see here this is the shear plane along which the deformation will takes place. So the force which act along this surface is known as the shear force, Fs. Now one force will act normal to this shear force, which we denote with the help of Fn. Okay, so you can see here this force is extended and it is specified here, Fn. Okay, now we come to the cutting force. So cutting force will be in the feed motion direction. So you can see here this horizontal force Fc, which is the cutting force, or we can denote it with the help of Fh also. Now one more force will act, which will be perpendicular to this cutting force. So you can see here Ft. Ft is our thrust force, or we can denote it with the help of Fv also. Fv is our vertical force. Clear? So all these forces are acting at this material. Now we can see here this is our T1. T1 is basically the uncut chip thickness, and here we can see this is the T2, means chip is flowing here, and T2 is as the chip thickness. Clear? So we have made an assumption that all the forces are acting at the tip of the tool, and now we are drawing one circle here like this. We can draw one circle here like this. Okay, and this circle, now all the forces are coming under this circle, and we can analyze these forces. So this circle is known as the merchant circle. Okay, this is the merchant circle. Okay. Now we will start the force analysis. So this is the same diagram which we have discussed in the last slide. So we can see here this angle. This is the phi, this is the shear angle, we all know. Now you can see here the angle beta, which is the friction angle, and this is between the friction forces F and N. So this is the friction angle, this is phi, alpha is our rake angle. Okay. Now we can see here this angle beta and minus alpha. So how we will get this angle? So if we assume that this value is x, so we can take this. Okay. So we can write here x plus this angle will become, this is beta, this is 90 degree. So it will become 90 minus beta. 90 minus beta plus alpha is equal to 90. Okay, so we will get the value of x here. X will become alpha minus, sorry, beta minus alpha. Okay, so this angle is beta minus alpha. Okay, now you can see some equations here. These equations are the force equations, means all the 6 forces which we have discussed here, these are having the equations. So there are 6 equations. Now we will derive these equations with the help of this merchant circle. So you should learn or remember all these equations. Okay. So first of all, we will do the derivation for Fs or Fn. Okay. So we have to remember the merchant circle, and we will see that what type of forces are involved in these equations. So we are talking about the Fs or Fn, means this is the shear force and the force which is normal to shear force. So these forces are involved. Okay. Now the Fc and Ft means cutting force or the thrust force are also involved. So from the merchant circle, we will take 2 triangles which are containing these 4 forces. So Fc and Ft. So we can take this triangle. Okay, and then we want to find out the Fs and Fn. So we can take this triangle also. Okay, so we will take these triangles and we will find these two equations, Fs and Fn. Okay. Now what we will do, we will draw these 2 triangles here. Basically, first we will draw Fc and Ft. Okay, this is our Fc, this is our Ft. Okay. After that, what we will do, we will draw, this is our resultant R. Then we have the shear force also. So this is basically Fs, shear force, and we have a line like this. So this is the Fn. Okay. These are 2 triangles which we have taken from the merchant circle. Now what we will do, for example, this is point A, this is B, and this is D. Now we have already find out this angle is beta minus alpha, this is our phi. Okay, and this is point F. Let's assume that this is point F. Now we will extend this line. Okay, and we will meet this line also if this point is C. Okay, and we from B we will take a perpendicular, or we will draw a perpendicular on the DF, and we are assuming that this is point E. Okay. Now this triangle is like this diagram. In this diagram, basically CF is parallel to BE and EF is parallel to BC. Okay. So this is our diagram, and we will use this diagram to find the equation. So first of all, we will consider our first equation, that is for Fs. So what is Fs here? We can write Fs as the AF. Fs is AF. We can write down Fs as the AC minus CF. AC minus CF. Now, as CF is parallel to BE, we can replace CF to the BE. So, we can write down AC minus BE. Clear? Now, we have to find out the value of AC and BE. So, for finding out the value of AC, we will take the triangle ABC. So, in triangle ABC, okay, in triangle ABC, we will find out the value of cos phi. So, cos phi will become AC minus FC. So, we can write down the value of AC as FC cos phi. Okay. Now, for finding out the value of BE, we will take the triangle BDE. Okay. And the value of sin phi in triangle BDE will become BE divided by FT. Okay. So, we can find the value of BE as FT sin phi. Okay. So, we have find out the value of AC and BE. Now, the FS is basically AC minus BE. Okay. So, FS will become, what is the value of AC? AC is FC cos phi and BE is FT sin phi, which is similar to our first equation. So, in this way we can find out any equation. Okay. Okay. Now, we come to the next equation, that is for Fn. So, we will again draw the same triangle. We will take the same triangles. This is our FC and this is our FT. Now, this is our FS and there is a line over here. This is A, this is B, this one is F. Now, we have extended this one up to point C and we have extended it here. Okay. And we will draw a perpendicular over here and this is E. Clear? And this is D, this is R, this is R phi, this angle is beta minus alpha and this angle is phi. Okay. So, this is our diagram. So, first of all, we will go for the Fn. So, how we can write Fn? Fn is basically Fs, this one is the Fn. So, Fn is basically df. So, we can write down df as de plus ef. Okay. Now, we know that here we will write DE plus EF is parallel to BC. So, we will replace it with BC. Okay. Now, what we will do? We will take different triangles and we will find out the value of DE and BC. So, first of all, we will take the triangle BDE. So, in triangle BDE, what will be the value of the cos phi? Cos phi will become DE divided by FT. Okay. So, we can write down DE is equal to FT cos phi. Okay. Now, we will find out the value of BCE. So, for this we will take triangle ABC. So, here the value of sin phi will be BC divided by FC. So, value of BC will become FC sin phi. Now, as we know that Fn is equal to DE plus BC. So, we will put this value here. Fn is equal to FT cos phi plus Fc sin phi, which is similar to second equation. So, we derived these two forces with the help of merchant circle. Okay. So, in the same way, we can derive for other forces also. So, now we are considering the force F and N. Okay. So, what we will do here, we will take the another diagram here. Okay. This is our Fc and this is our Ft. Clear? And this is our F. We will see what type of forces are involved here, and this will become N. Okay. This will be our beta and this will be, if this point is A, then this will become alpha. Okay. This is our, we will take like this. Okay. This is our beta minus alpha. Okay. And then again we will draw a line over it and we will make a perpendicular E here. This is B and this line will be parallel to this. This line will become F and this point will become D and this, okay, this is N, this is point G, this is R dash. So, in this diagram we can see here we have taken two triangles which are having the forces Fc, Ft and F and N, because these forces are involved in this equation. So, we will see, we will take different triangles as we have done in the previous slides and then we will find out the value of the cos alpha or sin alpha, and with the help of those we will derive these equations. So, what we will do for the first equation, so for the first equation, for the F, we can write down F as the AG. F is equal to AG here, and as we know that AG is parallel to CD and okay, AG is parallel to CD and we can write down the CD as the CE plus ED. Okay, CE plus ED. As ED is parallel to BF, we can replace the ED CE plus BF. Now we will take the triangles and we will find out the value of CE and BE here. Okay. So, if we take the triangle BCE, then what will be cos alpha? Cos alpha will become CE divided by Ft. Okay. So, we will find out the value of CE as Ft cos alpha. In the same way, when we will take the triangle ABF, so what will be the value of the sin alpha? Sin alpha will become BF divided by FC. So, we can write down BF as FC sin alpha. Okay. So, what will be the value of F? F will become Ft cos alpha plus Fc sin alpha. So, this will become our equation. Okay. Okay. Now, we will do the derivation for this equation N. So what we will do, we will again take the same diagram and we will find out the value for okay. This is F and this one is N, and this angle will become beta, this one will become alpha, this is E, this will become beta minus alpha, this will become alpha. Okay, we are taking the same diagram here. This point is D, this is F, this one is B, and this one is C, this one is G. So now we will do it for the N is equal to CG. So we can write down CG as the AD, and we can write AD as AF minus DF. Okay, AF minus DF. Now FD and BE are parallel to each other, so we can write it like AF minus BE. Okay, so in this case also we will take different triangles and we can easily find out this equation. Clear? So I am skipping this one. Now if we consider mu as the coefficient of friction, okay, if mu is the coefficient of friction, so we can write down mu as tan beta, because beta is the friction angle. We can write down mu is equal to tan beta, and which will become F by N, and we have put the value of F and N here. Okay, now what we will do, we can convert it in terms of the tan alpha. Okay, so we can write down Ft plus Fc tan alpha divided by Fc minus Ft tan alpha here. Okay, now if we talk about the shear area, okay, so I am drawing here the 3D view. Okay, this is our basically, this is our workpiece. Okay, now this area is, this is basically the shear plane, this one is the shear plane. So this angle will become phi and this distance will become chip thickness, okay, T1. Now this is the plane along which the shear force will act, Fs. So this area is known as the shear area. Okay, this area is known as the shear area. Now if D is the width of this workpiece, okay, so we can write down AS. AS is your shear area. So shear area will become B into, means width, divided by T1 by sine phi. So this will become the shear area. Now we can find out the shear force also. So shear force will become Fs is equal to tau into As. Okay, and we can write it like tau into B into T1 divided by sine phi. So shear area and shear force. Clear? So what is tau here? Tau is basically the mean shear stress. This is the mean shear stress in the shear plane. What is B? B is the width, okay, and T1 is the uncut chip thickness. Clear? So if we here we were talking about the shear force. If we talk about the normal shear stress, sigma, so sigma will become Fn divided by An, or we can write down As, because An or As will be similar. So Fn will become sigma into B into T1 divided by sin phi. Okay. So what is sigma? Sigma is basically the mean normal stress. Okay. Okay. Now we have the two equations, Fc or Ft. So Fc is basically our cutting force and Ft is our thrust force. Okay. So we have the equations like by equation Fn. Fn equation was this. So by putting this in the equation 3, this is equation 3. So we will put the value of Fn here. Okay. So we will get Fc is equal to this. Okay. And we can do the same thing for the Ft also. Ft will become Fn cos phi into tan phi plus beta minus alpha minus sin phi. So we will get these two equations for Fc or Ft. So when we will rearrange these equations, we will get Fc is equal to Fs cos beta minus alpha upon cos phi plus beta minus alpha, and for Ft we will get Ft is equal to Fs sin beta minus alpha upon cos phi plus beta minus alpha. So these are the equations which we get from the merchant circle, and we have already discussed this. Shear force is tau B T1 by sin phi. Okay. Now merchant determined the phi. Phi is our shear angle. Assuming the minimum energy principle, means the minimum energy was required to deform the material along the shear plane. Okay. So this condition, for the minimum energy conditions, what it will become basically okay. As per these conditions, we will differentiate Fc cutting force with respect to phi. So what we will get? We will get here tau into B into T1 cos beta minus alpha cos 2 phi plus beta minus alpha divided by sin square phi into sin square phi into cos square phi plus beta minus alpha, okay, is equal to 0 as per this, or we can write it like this will become cos 2 phi plus beta minus alpha is equal to 0, or we can write down 2 phi plus beta minus alpha is equal to 90 or pi by 2, okay, or phi is equal to pi by 4 minus half beta minus alpha after simplification, okay, and this 2 phi plus beta minus alpha is equal to pi by 2. This equation is known as the merchant first equation. Okay. So, this is all about the force analysis, merchant circle and the merchant first equation. So, these are the references. So, thank you so much.